Thank you everyone for joining this virtual Mine Walk lecture series. My name is Monica and I'm with the Central Coast State Parks Association, or CCSPA. We are the nonprofit partner to the state parks in San Luis Obispo County, and we help fundraise for their educational and interpretive programs offered throughout all the parks, from Oso Lake in the south up to Hearst San Simeon State Park in the north. And the Virtual Mine Walks lecture series is just one of the many educational opportunities offered by state parks. This series happens twice monthly on Fridays. We have subject matter experts talk about all sorts of things relating to the Central Coast and the state parks within them. And we're very excited to have Dr. Antonio Garcia here today to talk about the geology of Montaña de Oro. Just a couple things before we get started. Today, you'll be able to ask questions via the chat or the Q&A feature. So at the bottom of your screen, you should see either of those buttons. Feel free to type questions as you think of them, and we will get to them at the end of the presentation. Also, this will be recorded. So if you need to head out early, or if you'd like to pass on this lecture to a friend later on, it will be uploaded to the State Parks YouTube page by the end of the month. And if you're signed up for our newsletter, you'll be getting those links once they come out. So I'm going to go ahead and stop sharing this. Oh, the links on the screen, I'll put them in the chat as well. That's where you can find out our upcoming lectures, as well as view recordings of past ones. All right, so today's presentation is called Landscape Development at Montaña de Oro. This talk will identify the erosional and constructive processes that have shaped the coastline at Montaña de Oro State Park. A survey of the plate tectonics of San Luis Obispo County will provide the context necessary to understand the interplay between mountain building, erosion, and sediment deposits that have produced textbook quality examples of coastal features. And we have with us Dr. Antonio Garcia from Cal Poly. He is a geomorphologist. Geomorphology is the study of the processes that shape landscapes from a geologic perspective. He earned a BS in geology at San Jose State in 1994. His MS thesis, earned at the University of New Mexico in 1996, is based on the geomorphology of the Dozy Wallops River drainage basin in the Olympic Mountains of Washington State. His PhD was completed at UCSB, and his dissertation is based on the geomorphology of the Rio Andarax, which drains the southern flank of the Sierra Nevada of southern Spain in the Almeria province. Antonio was hired and started teaching at Cal Poly in fall 2001. Since 2003, most of his research has focused on the geomorphology of stream valleys within the San Andreas Fault Zone in Monterey and San Luis Obispo counties. More recent work includes documenting and assessing landslides and landslide hazards in Poly Canyon, as well as investigating recent fault activity in the Mojave Desert. Thank you so much for being here, and I'll go ahead and let Dr. Garcia take it away. Thank you very much.
Thank you very much, Monica. Let's see. Okay, and thank you, Monica, and thanks everyone who's joining us here today. I'm still very much infatuated with the geology and tectonics, really, of San Luis Obispo County. It's really an amazing place. There's been a lot of work done. Most of what I'm presenting is work that was done by someone named Catherine Hansen and William Lettuce, who were hired to assess the seismic hazards of the area by PG&E to make sure the nuclear power plant was okay. And this work was completed in the early 90s. And so they really did a great job. And I'm basically summarizing their work. I've done some research on mountain building in the Central Coast, but it's a little bit farther up in Monterey and doesn't really apply to what's going on here. But so I'm doing the geology of Montaña de Oro, but it's more the topographic development. I'm not going to get much into the rocks, if at all. It's more the landscapes and how they look, because as Monica informed you, that's what I do. I'm a geomorphologist. So anyway, here it is. There's the view. And just a quick talk outline. First, I'm going to talk about plate tectonics and mountain building in San Luis Obispo County. And really this idea, there's actually a paper written by, they Lettuce and Hansen and Lettuce, they swap back and forth. They have published a bunch of papers, and they have a paper exactly about what I'm presenting today, which is how just the strong influence of tectonics and faulting on the coastlines in San Luis Obispo County. Okay, so off we go. So I'll start off with plate tectonics. And this is kind of a little bit of a sloppy figure, but it shows more or less what's going on. So here, I'm going to use my cursor as a pointer. So here's the San Andreas Fault right here, denoted right there. You can see it right there. Okay. And what's going on here now today is that the plates aren't moving perfectly parallel to the plate boundary. So there is a component of convergence across the plate boundary, and that's what has led to mountain building. Right? Mountains grow when tectonic plates crash into each other. Because there's a collision, the Earth's crust gets thicker and shorter, and it makes mountains. That clearly, there has to be more going on here because the San Andreas Fault is a strike-slip fault, so the plates are just moving past each other. And what's going on is there's this oblique convergence across the plate boundary, and that's what's causing uplift of the mountains in San Luis Obispo. So here's a little bit of a historical perspective on it. And this is an animation produced by Tanya Atwater at UCSB, who I'm lucky enough to have had as a mentor when I was there. And so what we're seeing here is the plate tectonic setting about 30 million years ago. Here on the right, this is millions of years ago. So actually, it's about 38 million years ago. And so this red line right here with triangles is what's called a subduction zone. And that's an area where one plate, in this case, the Farallon plate, gets stuffed beneath the North American plate. And that's kind of what we see here. This red line right here is a seafloor spreading center. Okay, so at this time, 38 million years ago, there was a plate called the Farallon plate that was separated from the Pacific plate by a seafloor spreading center. These white arrows show the motion of the Farallon plate and the Pacific plate relative to the North American plate. So sort of for a reference frame, North America is held fixed, and we see that the Farallon plate is converging with the North American plate. And then there's the Pacific plate out here, which is separated from the Farallon plate by a mid-ocean ridge. And notice that the Pacific plate is moving differently than the Farallon plate, whereas the Farallon plate is converging with North America, the Pacific plate's moving away from it. So here we go forward in time. So this was, here we go forward. And then notice right here, right, the seafloor spreading center gets subducted so that the Pacific plate comes into contact with the North American plate. And although the Farallon plate, which its remnant is known up north as the Juan de Fuca plate, although that was converging with North America, the Pacific plate is moving kind of up and away from it. So that's when, at this time, once that seafloor spreading center got subducted, that's when the transform plate boundary formed, or the strike-slip boundary, which we today know as the San Andreas Fault. Okay, so we go forward in time, and here we see, so now we see, again, what geologists call a transform plate boundary, which is where plates move past each other. That's when that history starts. And then right about here, so this is blocking me. So right at about, so I'll let it run all the way through this time. So our story starts really here. So now we have a time when there's the Pacific plate, a substantial part of the Pacific plate is in contact with the North American plate. The plates are moving past each other. This transform plate boundary is established. But notice that the Pacific plate is moving kind of a little bit away from the North American plate. And that causes what geologists call extension, which is a thinning of the Earth's crust, which leads to development of low-lying areas. And so it was at this time when the rocks we see in the beach cliffs at Montaña de Oro, they were deposited in this time. That area was entirely underwater, about from, starting 20 million years ago up until about 5 to 8 million years ago, it was underwater. And that's when the rock unit is known as mostly as the Monterey Formation, and that's what accumulated. And those are the strata you see in the rock in the beach cliffs. That's when those rocks formed. So that's about as much as traditional and rock geology I'm going to talk about, but it seemed important. So then we move forward in time, and look what happens right at about 8 to 10 million years ago. Okay, right there, the arrows, animation. Okay, so now I lost my cursor. Sorry. Okay, so notice there's a change in the way the arrows are pointing. Okay, right at about 8 million or 10 million years ago, the motion changes, and the arrows are now showing the Pacific plate, the motion of the Pacific plate relative to the North American plate changed. And so at that point, that's when this oblique convergence I was talking about started to happen. And that started about 8 to 10 million years ago. There, the numbers are kind of funny. It depends where you look, you get different numbers. But generally, the story of the mountains, when they started rising up, when this area changed from being underwater, because it had been thin, to now emergent, because the plates are converging with each other across the plate boundary, that history starts at about 8 to 10 million years ago. And that's when the mountains around here started growing, basically. And here's a figure showing sort of a summary of, this is a cross section through the Central Coast, drawn pretty much precisely right through Cal Poly's campus, believe it or not. And it's very cartoon-like, but it's very effective. So this shows that this dark arrow right here shows the motion of the Pacific plate relative to the North American plate, right? Notice it's not perfectly parallel, and there's just this little bit of convergence, right? If we break the motion into vectors, this is the vector that's showing how much convergence is occurring. So there's just this little bit of convergence, but it's enough convergence to create mountains, okay? And so here we see faulting where some blocks are rising and others are sinking, okay? And these are what are called, they're called what we call reverse faults. And I'm gonna talk about those later, so we need some terminology now. So a reverse fault, this is called the hanging wall, and this is the footwall, as you can see down here in this nice color figure. So when there's a reverse fault, the hanging wall moves up relative to the footwall, which moves down. Okay, so this is essentially the structure of San Luis Obispo County, you know, very simplified into a cartoon. And because of this oblique convergence, there's blocks of the crust that are rising, like this one, and others that are sinking down, like that one. Okay, and that's the consequence of this oblique convergence across the plate boundary. Here's another more simple figure showing it just a little bit differently. It's just a straight cross section. And so this is the San Andreas Fault here, which is vertical. And the T means the block over here on this side of the fault is moving toward you, out of the screen. And the A means this is moving away from us into the screen because it's a strike slip fault. And then here it shows a series of faults, of reverse faults, where some blocks are rising and some blocks are sinking. Okay, so that's the a nice tectonic summary of what's happening in this area as the consequence of this oblique convergence. It's called strain partitioning, where the strain is partitioned into faults that make things move up and down and faults that allow things to move past each other side by side. Okay, and so the effect of this is the topographic pattern that we see in the Central Coast. So here's the San Andreas once again. Okay, and then the areas shown as these sort of lines, hotchers they're called in geology, I think. This is positive topography, or areas that are up high, and then the white areas are areas that are down low, right? So here's the Los Osos Valley, here's the San Luis Range. So obviously we're going to focus on this right here, right? The San Luis Range. It's pretty nice because this is where all the expression of the strain partitioning and the oblique convergence and the faulting, it all is pretty much best expressed right here. And luckily that coincides with Montaña de Oro, so it makes for a nice story. So here we can see the positive topography, so to speak, where there's mountains, and the low-lying topography where they just leave it as white area, a white area. Okay, and then here's what it looks like in all its glory. In an aerial, this is digital data, believe it or not. This is a digital elevation model. And so here we see the San Luis Range, Montaña de Oro is right here. Here's the Sandspit, the Los Osos Valley, and then here's the Santa Lucia Range, and here's the San Andreas way out here. So it's kind of remarkable if you think about it, but that's what plate boundaries do, and that's what plate boundaries are. They're kind of remarkable places on the planet where mountains grow. And being someone who grew up in South Florida, which is as smooth as a pool table for hundreds of miles in all directions, I'm still like, I think that's why I'm still infatuated with somewhere like this, where there's this incredibly interesting topography, and it's all related to the plate boundary out here, right? The oblique convergence is leading to uplift of the Santa Lucias over here, the San Luis Range here, the Casmalia Hills down here. And these uplifted areas are separated by these low-lying areas, because that's what happens when reverse faulting happens. Some blocks move up and some move down, okay? And so here's zooming in a little bit into the sort of San Luis Range. They're calling it here the San Luis Pismo structural block. And so here we see, this is called the Los Osos Fault Zone, which extends from, you can see this is Arroyo Grande Creek. So Highway 101 is right about here. Costco is like right about there, which didn't exist when this map was made. and there's a fault zone that extends along the base of the Irish Hills / San Luis Range. And so this block is rising up, and this block here, which is basically, they call the Los Osos block, or I guess they're calling it, this is the block that's sinking down along this fault zone, and this block is rising up along that fault zone. Okay. And so here's just what it looks like from various places in the county. This is a view from East Cuesta Ridge. And so the Seven Sisters is kind of a whole nother element that makes it a little bit confusing, but it's not so bad. Essentially, the Seven Sisters, right, here's, I believe this is Cerro San Luis, also known as Mount Madonna, Bishop's Peak, and so on the way down. So these are high standing because this is composed of rock that's relatively hard, that sort of fed volcanoes that used to be at the surface, and they solidified. So everything's been eroded around them, so they're standing up high. But that's kind of a different story than the one that we're talking about, where here we see the San Luis Range, which is rising up along faults, and then the low-lying area adjacent to the San Luis Range. And that low-lying area happens to have these high peaks that are formed in relatively resistant rocks. Okay, so that's all this right here. Okay, and so here, the one thing that is nice, although they kind of, in a sense, ruin the story and make it a little bit sloppy, the Seven Sisters provide great overlooks for the story that we are telling. Okay, so here's, again, from Cerro San Luis, and here we can see this is Foothill Road right here, Los Osos Valley Road right there, and here's the San Luis Range. Okay, and then this is probably really small, but here's the Los Osos Fault Zone on the map. So the Los Osos Fault Zone extends all along this area right here, and it's raising this area over here relative to this area right here. Okay, and so the rising area in a reverse fault is known as the hanging wall, and the down dropping area is known as the footwall. Okay, and so here's a view also from Cerro San Luis. This is Laguna Lake. Okay, and then here is the San Luis block. So again, there's a fault zone that extends from this area right here, right across where I'm moving the cursor, all across the base of the range. There's a lake here, and so that lake is definitely not a natural lake, but it wasn't too hard to create. They just sort of impeded drainage here a little bit, and it became a lake because it's an area that's actively sinking. Kind of intuitively, when you think of, plate tectonics and plate collisions, like mountain buildings, mountains grow, and all this stuff happens, but really part of the expression of the convergence and faulting and convergence across the plate boundary are low-lying areas like this one, which can fill with water if they're sinking rapidly. So now here's a view from the San Luis Range back at Cerro San Luis, and here's that lake again. So this is the low-lying area formed on what we call the footwall right here of a reverse fault. And so we're standing on the hanging wall, looking at the footwall, and then there's Laguna Lake. Believe it or not, this is a picture from when it used to rain here. This is in February of 2010. And this is a view from the intersection of Foothill Boulevard and Foothill Boulevard and Los Osos Valley Road. And you can see that it's totally flooded. And again, it's an area that's subsiding actively, again, because this expression of mountain building and tectonism, the mountains are the spectacular example. And then, these are less glamorous, but it's a low-lying area, and it's sinking, sufficiently fast to become totally waterlogged when it rains a lot. And then again, here, just to visit the map once again, here's San Luis Creek. So this is the area that we're talking about right there. Hanging wall block rising up, footwall block sinking down. Okay, so that's the overall tectonics and faulting in patterns in this area. And what's really interesting at Montaña de Oro is where all of these structures, where these faults and these features intersect the coastline, and that ends up, what we just talked about has a huge impact on what the coastline looks like. Okay, so we need a little bit of background about how sediment is deposited on coastlines and the related processes. So we're going to do that now. Okay. Okay, that's what's happening here. Okay, so all right, so if we look at a map of North America, okay, so here's San Francisco, we're down here, and what's pretty striking if you look at the ocean is, if you've ever wondered why the surf in California is so good and the surf on the East Coast is kind of lousy and not nearly as good, it has to do with the continental shelf. Okay, so this area is shown in light blue is the continental shelf on the east coast of North America. So it's relatively broad, it's very wide. So there's this pretty extensive area offshore that has this gently sloping and shallow. So that kind of minimizes the wave energy that affects the coastline. Whereas here, it's a tectonically active area, there's a plate boundary, and the continental shelf is relatively narrow, and it's also relatively steep. So it's a lot easier for the waves to reach the beach, and then the surfers are all happy, of course, because they get bigger waves. So what you see on these areas, like on the East Coast, where there's this broad and shallow continental shelf, you get these things called barrier islands. And so if there's anybody out there that grew up on the East Coast or has been there, when you go to the beach, you always have to drive over a bridge to get to the beach. It's because the beaches are all formed on these barrier islands. And so these are, here's the barrier island where I grew up, and this is South Beach in Miami. This is called Government Cut, and there's a cruise liner heading out. And this is now an infamous place. They built all those hotels and they weren't really thinking, and the first one just collapsed. It was a condo, but anyway, it's very tragic. And so here we see these barrier islands on the East Coast. And there you expect that, again, because there's this broad continental shelf. And that's kind of what you expect in areas that have these big, wide continental shelves. So when we look at, the reason to bring all this up is when we look at Montaña de Oro and, you know, the estuary over here, it's like, why is there a sand spit? We have this steep shelf, it's tectonically active. Why is there a feature that is pretty much identical in terms of process and how they form is these barrier islands on the East Coast of North America? You can see they're pretty extensive. They're big enough to build hotels and condos, which you probably shouldn't do. And so here's our glorious sand spit. So a quick story about this sand spit. So I have a colleague that early in my career I collaborated on. He's from the UK, he's at Plymouth University, and I was taking him all around the county, showing him the San Andreas Fault. And he was always, you know, I'm like this all the time, and he's, you know, very low key, kind of, I think he did it on purpose. So I showed him all these rocks and all these places, and he's like, yeah, that's pretty good, that's pretty good. So I was like, okay, fine, nothing's here is that interesting. So we were just hiking out with the dogs, and we got this view, and it was an unsolicited request, and he said, that is a spectacular sand spit. So by any standards, our sand spit apparently is globally impressive. It's a very, you know, impressive sand spit. So why is it there? We have this steep shelf. Why do we have a sand spit here? Okay, remember, wide shelf, sediment can accumulate because there's relatively low wave energy. Steep shelf, it's unusual to have sediment accumulate offshore because there's waves coming in all the time, just eroding that sediment and taking it away. So why do we have a sand spit? Okay, one reason has to do with a process known as longshore drift or longshore current. So where we live, the waves, the predominant wave orientation or the predominant direction that waves come from is from the northwest. So what ends up happening is the waves come up against the beach and they kind of swash up this way and down that way and up this way and that way. So ultimately what happens is there's a current that forms adjacent to the coastline within about 1 kilometer of the coastline. And as it says here, there's a net movement of sand grains. So the longshore current's going this way, and it creates something we call a littoral cell. Littoral is kind of an archaic word that has implications of coastlines. So it's a littoral cell, so it's like this package of sediment that moves down the coastline. And so that's what happens on any coastline. You know, depending on the direction of the incoming swells, you get this longshore current that transports sand along the coast. When there's an embayment like this one, what happens is that the waves are bouncing off, they establish this longshore current. But here, where there's nothing for the waves to bounce off of, then the littoral cell is disrupted and sediment gets deposited. And it's shown here as a growing spit. Here it's shown as a baymouth bar. So where there's an embayment, the littoral cell is disrupted and the longshore current is disrupted. So you get accumulations of sand. Okay, so one reason why we have this formidable sand spit is because here's the Los Osos fault zone, right? And remember, this is the block that's sinking down. It's the footwall block of a reverse fault, so it's sinking down. We saw all those pictures of the water accumulating way back over here. At the coastline, it allows the ocean to invade farther inland because it's sinking downward, right? So it just creates a low-lying area and the ocean invades a little bit farther, and that creates this embayment, which we know and love as the Morro Bay Estuary. And then there's the sand spit. So the fault zone, the Los Osos fault zone, comes across kind of right here. This block is sinking down where my cursor is, and it created this embayment, which disrupted the transport of sand and led to deposition of this sand spit. Okay, here it is And so that's one of the factors that has led to accumulation of sand in what we call our beloved sand spit. It's probably better called a bay mouth bar, but that doesn't sound as good. So we can just call it the sand spit, like everybody calls it. And that's why it's there. So that's one reason why we have a sand spit. Or it's kind of one requirement when geologists look at a coastline. Okay, why, what factors influence sediment deposition? One factor can be, in this case, faulting at the coastline, which creates an embayment, and it leads to disruption of the littoral cell. Another reason why we have this wonderful sand spit is because there's a huge amount of sand delivered to the ocean, just up coast. Remember that the predominant direction of swells coming into the coastline is from the northwest, so the Longshore Drift is pretty much always to the south around here. And here, this is kind of a very lousy map. It shows all these roads, but the roads, keep in mind, there's always, all these roads are built in valleys that have streams. So there's all these streams draining the Santa Lucia Mountains and sending all this sediment to the coast right there. And it moves down the coastline, it encounters this embayment, the littoral cell is disrupted, and we get the sand spit. So here's just some pictures of that. This is off of Toro Lane, Morro Bay. And you can see it was a rainy day and there's water coming out of the culvert. And notice it's kind of brown, there's some sediment there. This is Toro Creek. This is a long time ago. And this is, if you're familiar with the dog beach in Morro Bay, this is usually, well, right now you can walk across it, but this was what it looked like on a huge storm way back when it used to rain here. And this is what it looked like as well. Notice there's a huge amount of what we call suspended sediment in the water because the rivers are sending all this, it rains in the mountains, that causes the rivers to flow, the sand in the stream beds are swept out into the ocean. And once they reach the ocean, they're available to move down the coast as this littoral cell. So this is what the water looked like. This was a huge storm. Notice all the debris, the broken trees and stuff that came from up the coast. And this is what it looked like from the big hills, sort of the Nutmeg area above Morro Bay. And there it is right there, a beautiful littoral cell. Notice that, again, it's within about 1 kilometer of the coast or less in this case. And here's all these rivers send the sand to the coastline and they're taken up in the littoral cell and they move down the coast toward the sand spit. This is a really remarkable picture. Sadly, I don't remember the student's name. For extra credit in my class, the students they can go to the sand spit and take a picture of themselves with the sand spit. This student happened to have a pilot's license, so he did it from the air and he gave me this photograph. And here's the sand spit, and you can see right here these little wisps of sand moving. You could even tell just by their shape, they're moving down the coast this way. And they're what nourishes and feeds our glorious sand spit. And there it is right there. And again, so remember, faulting at the coastline over here created the embayment. Now we have all these rivers sending sand to the coast, and that river, because it's disrupted here at the embayment, accumulates as a sand spit. Okay, and so there it is one more time, our sand spit. Okay, so that's how that explains this part of Montaña de Oro. I suppose it's more the sand spit than Montaña de Oro, but the sand spit is officially in Montaña de Oro, so I think it's appropriate. And so now we understand what's happening here, right? I guess the park probably comes to somewhere, I don't know, around here. And remember, there's a fault zone. Now we know there's a fault zone that comes right through here. It's created this embayment, the sand spit's deposited. So now let's look at what's going on over here, which is actually even more interesting and spectacular. Okay, so there's features geologists call marine terraces, and they're very common in California. This is up at the Kenneth Norris Rancho Marino Natural Reserve in Cambria. And this is a marine terrace. Much of the California coastline looks like this. These are called marine terraces. We're going to get into how marine terraces form and exactly what they are in just a few minutes. Here's another view of this same location, the Kenneth North Natural Reserve. It's a UC, part of the UC reserve system. So everyone's probably seen this. If you've spent time on the coast in California, this is what it looks like. There's this, people call them coastal bluffs or whatever, the marine terraces. This is a view of Carpinteria, south of Santa Barbara, or I guess it would be east of Santa Barbara. Nice, beautiful marine terrace right there. And of course, this is actually the same student who was a pilot. You can see the pilot wing right there. This is the Diablo Canyon area, kind of, so that would be south of Montaña de Oro, but really, really spectacular marine terraces, really nice ones. Okay, so let's look at the kind of nuts and bolts of a marine terrace. Kind of the base of a marine terrace is what we call a shore platform, or once it becomes a marine terrace, it's an uplifted shore platform. Okay, so this is at Jade Cove up on the Big Sur coast, and these are metamorphic rocks from very deep levels brought to the surface. And then right there, you see how there's that very abrupt contact between these rocks, which are greenish, and then a bunch of sediments up here. Okay, so this is what's called an uplifted shore platform. Okay, here is an active shore platform. This is just north of Cayucos. And what happens is, as waves come in and approach the coastline, right, they encounter shallow water. Ultimately, they turn into breakers, and those breakers bevel off or carve this smooth feature along the coastline. And the tools they use to carve these features are gigantic boulders like this one, or even smaller gravel like this also plays a role. So the constant wave action of these waves breaking on the coastline erodes this bench right at kind of the high tide line, and it extends for some distance below the high tide line. And that's what's called a shore platform. And so you're saying, okay, here's another shore platform also just north of Cayucos. And you might be thinking, well, that doesn't look smooth at all. I agree, it doesn't. Here's a near Goleta. Sometimes they're not so smooth, but if you zoom out, this is Cape Perpetua in Oregon, right? If you look up close, it's going to be rough, but if you zoom out, overall, it's a pretty smooth surface right here. So here's the modern active shore platform being carved, not right now, but when high tide comes in, it's surely going to be carved and being eroded. And if you zoom out far enough, it is essentially a smooth surface, right? We're talking about a scale issue here. If you look at it on a big scale, it's a very smooth feature, and we call that a shore platform. Sometimes they really are smooth. Some people call them wave cut platforms. So here's actually a very nice smooth shore platform. This is somewhere in Bolinas Point up the coast. So this is in San Simeon in the Hearst property area. So this is absolutely spectacular. So here we see the active, truly smooth shore platform right here. And then here's an uplifted shore platform right there. Okay, so this forms at sea level at the high tide line right there. And then it gets uplifted later and becomes a marine terrace. And here's the sediments that overlie the shore platform. And so now this is what we call the marine terrace, the shore platform and the overlying sediments, right? So this is a marine terrace, and this is the actively forming shore platform. Here's a view in that exact same spot, standing on the uplifted shore platform, looking down at the one that's being carved right now. And then for a little kind of, got to have a little bit of drama here. So this is a day when there was what surfers call triple overhead waves. They don't look that big in the video, but there were huge waves at this very same location. And you can actually see this rock in the video, and it kind of highlights or underscores how the waves crashing into the coastline bevel off this smooth feature, which we call the shore platform. So here it goes. So here comes a big wave. And think of the rocks being picked up by those waves and smashed down against the rocks and carving the rocks kind of day after day, storm after storm. And that is how a shore platform is produced. Okay, so there it is. And then, of course, here are the absolutely everything in Montaña de Oro just defies description. It's just spectacular shore platform. So here we see the shore platforms, the modern shore platform. This is Spooner's Cove. So modern shore platforms. Here we see the uplifted shore platforms right there. Here's sediment, and here's a contact with the rocks down below. The Monterey Formation is the one that formed when the area was below sea level. Right now, that rock is being carved into these shore platforms, and some of those shore platforms are uplifted, and they form marine terraces. Okay, so to talk about the complete process by which marine terraces form, I want to talk about sea level fluctuations and climate fluctuations, because what to me, what's kind of, sounds melodramatic or over exaggerated, what's really sublime about marine terraces is that they're these incredibly orderly feature, right? They're these nice, smooth, planar features that get uplifted and make these stair-stepped coastlines. And the way they form involves two completely unrelated processes. So in a way, it's kind of like the ultimate example of serendipity, where these two completely unrelated processes converge and collaborate to make these beautiful forms on Earth's surface. So this is just illustrating something that probably everybody's very aware of now, but the Earth's history had periods when there's a lot of ice on the planet. We call those glacials, and when the ice melts, we call them interglacials. So 18,000 years ago, that's what this means right here. 18 Ka means 18,000 years ago. This was at the maximum advance of glaciers during the last so-called ice age, or the last glacial period. And what we're going to see is that as the ice melts, sea level rises. And so the point that's being made here is that glacial periods and interglacial periods cause sea level to rise and fall. And that's a fundamental element in the production of marine terraces. So here we go. This is just fun too. This is another tiny outwater video. And here we see sea level rising. This is the Bay Area, of course. And 11,000 years ago, there it goes. And then we go forward in time. The Bay Area is nice and wet. And then right about now, Europeans arrive and suck all the water out of the Bay Area. And anyway, there it went. Okay, so that's just illustrating this idea of sea level rising and falling as a consequence of climatic fluctuations, which influence the amount of ice on the planet, which influences the amount of water in the oceans. So now here is another animation from Tanya Atwater showing the process. Okay, I'll just let it, well, I'll narrate once and then we'll watch it. So here we see a low stand of sea level. Now there's a high stand of sea level, right? So there's the shore platform being carved up there. Sea level drops. Okay, then it stays down here for a while. And now is when it gets exciting. Okay, so here we go. So here comes, so there we see a shore platform being carved during the low stand of sea level. Now we have a high stand of sea level with a shore platform being carved. Right there it is right there. And then sea level drops, then tectonic uplift occurs. And if that shore platform is raised above the level of the next high stand of sea level, then it becomes a marine terrace. So there's one, here's another one that formed, right? Sea level drops. Okay, it rises again. That was raised above the next high stand of sea level, so it's preserved as a marine terrace. It drops again. Here's another marine terrace, as long as it doesn't get out. And there it is. You build houses on it, and beach cliff collapse happens, and there it goes. So Tanya has a sense of humor as well. This is supposed to be Santa Cruz, I'm pretty sure. So let's watch that one more time, as Tanya would say. And this is it. This is how marine terraces form during these high stands of sea level. Shore platforms are carved. If they get uplifted sufficiently to stay above water during the next high stand of sea level, they get preserved as marine terraces. And there it goes, one more time. And here we go, tectonic uplift. That's what the big arrow represents. And there it is. Okay, there it goes. One more. I have to see that one twice always. Okay, and so here's just some examples of marine terraces. This is appropriately enough, because the previous video was based on Santa Cruz. This is the Swanton Pacific Ranch, if people know what that is. It's a property that was donated to Cal Poly. It's up near Davenport. This is a concrete plant at Davenport, if you're familiar with that. And here we see one terrace level, another terrace level, another terrace level. So these are pretty spectacular up in Santa Cruz. This is this is Palos Verdes Peninsula in 1958, and notice this spectacular marine terraces that exist there. Now it's all completely paved and you probably can't see anything, but it's a good picture nonetheless. Okay, so there's kind of a recipe we can talk about for marine terraces that we see today. So we're in a high stand of sea level, so pretty much all the terraces we see form during high stands of sea level, and that'll become important in a second. And so step one, wave action at the coast carves a shore platform during an interglacial period during the high stand of sea level. Beach rocks and boulders are the cutting tools that carve the shore platform. Sea level falls during a glacial period or a low stand. And during that low stand, if uplift of the coastline is happening, and if the shore platform is raised above the level of the next high stand, then it gets preserved as a marine terrace. Okay, and that's how they form. And so here we are now back to Montaña de Oro and my fantastic student, the pilot. So here we see the modern active shore platform being carved at low tide. right? On high tide, it would be underwater. Here we see one uplifted shore platform and one marine terrace. Here's another one right, well, actually there's one right here. There's another one here. And Montaña de Oro, it really is a special place. Probably, south of Santa Cruz and to at least as far as Ventura and probably well beyond that, there is no other sequence or flight of marine terraces as extensive and well preserved as the ones at Montaña de Oro. Here's a nice sort of another pilot picture. One terrace level here, another one here, another one here, and another one there. And that's if you've ever hiked to Valencia Peak and you notice the trails like really steep and then flat and then really steep and flat, you're basically hiking up a sequence of marine terraces. And one thing that's really nice about marine terraces, from a geological perspective, if it's something you want to study and you want to figure out, for example, how fast the mountains on the coastline are rising, we can be very confident because we're at a high stand of sea level right now. Sea level is as high now as it's been for the last 1.5 million years, roughly. So if you see a shore platform above sea level and the corresponding marine terrace above sea level, then it has to be a high stand shore platform. And we have a very good control on when the high stands have occurred. So the folks, again, the work of Kathryn Hansen and William Lettuce, they estimated the age of these terraces at Montaña de Oro. The youngest one is about 80,000 years old. This one right here, which isn't that well expressed, is about 120,000 years old, 210,000, 330,000. And then the highest ones were just like these tiny little bits and remnants. Those are about almost 500,000 years old. And you might be saying, well, how can that be a marine terrace? How do they know? They hiked it up there. They found the gravels that were clearly beach gravel. It's pretty easy to recognize. A geologist can pretty readily recognize sediment that was deposited on the coastline. And so on its own, just the shape of this feature isn't that convincing, but they did find the sediments. And so that's the flight of terraces at Montaña de Oro. And so there it is. It's kind of it's a very much a yin and yang thing where we have a subsiding block, right? There's a fault zone we know comes right through there. This block is sinking down, and that led to deposit of to accumulation of sand as a sand spit, right? Then we cross the fault. This side's rising up. It's the hanging wall, and we see this spectacular flight of marine terraces, which is again at least from Santa Cruz to at least Ventura and probably beyond. It's the most complete and well-preserved flight of marine terraces on the California coast. So it's a very special place. And again, it's pretty much a textbook example of how faulting and tectonism can influence the morphology of a coastline. Okay, so that's it. That's all I have to present. If people have questions, stop the share. Okay.
Awesome. That was fascinating. Thank you so much.
Oh, you're welcome.
We did have a couple questions come through, and folks, if you think of any, feel free to type them in. First question, can you quantify the rate at which the Morro Bay area is sinking? And if so, how are you able to make that calculation?
Okay, so let me go back to can I share the screen again?
Yeah, go for it.
Okay, so share the screen. Okay, all right, it's gonna take a second. Okay, so first and foremost is what gives us the age control is the marine terraces. That's what's controlling, that's what gives us the rate at which the mountains are rising. Okay, in order to figure out a rate of mountain building or a rate of subsidence, there has to be a marker that can be dated. And in this case, the marine terraces have done that very generously, I guess we can say, if we want to personify marine terraces. But if we look at this, and let me go to full screen. If we look at this map, see these numbers right here, 0.2, 0.19, 0.2, these are uplift rates in millimeters per year along the coastline. And this is, again, the work of Kathryn Hansen and William Lettuce. So it's very, very difficult to calculate a rate of subsidence or sinking. That's almost impossible to do. Pretty much the best that we can do is look at these marine terraces, look at the rate of uplift of the mountains, and we know how fast the mountains are rising. And so remember, that's called the hanging wall block of a reverse fault. But as far as how fast the footwall of the reverse fault is sinking, that's really hard to calculate. And I don't think anyone knows, not precisely. They have some thickness of sediment in the Morro Bay estuary, and the difference in height of the, like if you match up features on this side of the fault with this side of the fault, there's been about 400 meters of faulting that occurred along the Los Osos fault zone. In other words, if you look at, here's a fault, right? There's a certain amount of throw or slip on the fault. The amount here is about 400 meters, and it's all relative one to another. So it's hard to say if it's absolutely sinking or not. When you're looking at fault slip, it's just one side relative to another. So unfortunately, I do not have an answer for that question of what is the rate of Morro Bay sinking. Right here, the 0.0, they concluded that it's basically, this is just staying, overall so within, again, there's just so much we could talk about. Within this idea of blocks rising and falling along faults, the whole area is also coming up. So even though it's a sinking block, it's also rising up to some degree. So if you combine the sinking along the fault and the overall rising, it looks like right here at this end of the sand spit, it's stayed pretty much 0 millimeters of uplift over the last few 100,000 years. So I'm sorry I couldn't answer that question any better, but that's a tough one.
I think that was a great explanation. Thank you.
You're welcome.
Couple other questions. With less rain, could the sand spit shrink due to less sand coming out of the northern creeks and rivers?
Potentially, yeah. I think that would be a reasonable, I don't know if assumption is too strong a word, but yeah, that would make sense if it rains a lot less. One thing that's interesting about, and this now gets into very much what my expertise is rivers. Like, things can be a little bit funky. Like, you might say, okay, it's raining less, so there's less water in the channel and there's less erosion. What ends up happening over long time scales, thousands of years, if it rains less, there's less vegetation. So in some cases, what happens, okay, overall there's less rain, but then there's these huge storms. There's more sediment delivered to the coast when there's these huge storms and there's very little plants. So that issue of sediment supply to the coast is very, very tricky and difficult to sort of estimate. But I think over, our time scales that are relevant to society, like years to decades, yes, if it rained less, I would suspect, over our lifetimes we could see some shrinking. But it seems pretty happy and healthy, and we'll see how the weather patterns play out. But I got a feeling. I know in 1994, I was in a seminar as a grad student, and they were pretty much everything that was predicted as a consequence of more CO2 in the atmosphere and global warming. It's all happening like exactly as these people predicted 25 years ago. And one of the things they predicted is, extreme weather, big droughts, huge storms, and it's exactly what we're seeing now. And I think it's going to be scary, but I think we're going to be seeing some big storms here eventually, and that'll keep that sand spit nice and nourished. Hopefully.
We'll see. Have there been any seismic events in the last 200 years that resulted in any visual uplifting or ground disturbance in the Morro Bay area?
No, not that I know of. The closest, the most active fault, and this is back to the Lettuce and Hansen map. I early in my career at Cal Poly, Kathryn Hansen, she owns a consulting firm, and someone that was a grad student in New Mexico when I was there, was working for her, and they contacted me and they came to visit, and I spent a day in the field with her, and she was amazing. She just knew everything. Okay. So, God, what was the question again? Just complete.
Let's see. Have there been any seismic events in the last 200 years?
The nearest that I know of, the nearest ground rupture is what maybe people are talking about in that question, or someone's talking about. The most recent ground rupture that I know of is right here at the Los Osos fault zone. Okay, so that's San Luis Creek. So it's pretty much right. If you've ever been on the intersection of Los Osos Valley Road and Foothill Boulevard, or if you're on Foothill Boulevard and you're waiting at the stoplight and you're going to make a right to go to Los Osos, if you look kind of across the road, there's a hill. It just rises up and there's these buildings. There's like that is actually an expression of faulting a fault that ruptured the Earth's surface. It happened within the last 10,000 years or so. That was again something that Kathryn Hansen and William Lettice discovered. My colleague at Cal Poly, who's a geophysicist, he got this new remote sensing equipment, and he wanted to test it. So he went out there to see if he could find the fault with his equipment, and he found it exactly where it was supposed to be. And again, that one, based on a whole bunch of stuff that would take a long time to explain, we know for sure it ruptured the Earth's surface within the last 10,000 years, which is, for what it's worth, the code now for being able to build a nuclear power plant in California is you can't have a fault that has moved within the last 100,000 years within 100,000 miles, a fault that has moved within the last 100,000 years. It has to be farther than 100 miles from the plant. So clearly Diablo Canyon would not exist by today's standards of seismic hazards. That's a loaded cannon, so I'm not going to say more than that.
Thank you. Questions keep coming in, so I'll keep asking them until you have to go. Where in the area are the oldest rocks exposed at the surface, and where are the youngest?
The oldest, probably, if you consider it the area on the Big Sur coast, those rocks up there, generally the oldest rocks are the part of what's called the Franciscan Complex, and that's it's Triassic, so it's about 140 something million years old. And the Franciscan Complex is all over the place. That's that green rock serpentinite. A lot of that is from the Triassic. I'll be honest, I don't have my numbers down exactly right for what the numbers are, but it's from the Triassic. And then up on the Big Sur coast, there's probably rocks that are comparable in age or a little bit older than that as well. Youngest, we have, it depends what you consider a rock, I guess. But there's a rock unit known as the Paso Robles Formation, and they still don't know the age, but they know it's relatively young, and that would probably be around 1 million years old or less. But there's a whole bunch of sediment that's been deposited as recently as a few thousand years ago in many instances. So the older rock question is actually a little bit easier than the younger rock question.
Thank you. Are there places on Earth that are along the same tectonic plates that have corresponding terraces, thereby allowing you to corroborate the timing of uplifting events around Morro Bay?
Yes, there are a lot, all up and down the California coast. The best record of marine terraces that they have used to calibrate all these types of studies is in the Southwest Pacific. And what's really special there is that there's corals, which can be numerically dated through carbon dating and other methods. There's corals in the marine terraces, and so they really nailed it down there, and that's allowed. And now there's other ways to date terraces. When Lettice and all these Lettice and Hansen, most of the papers are Lettice and Hansen, but when those papers came out, they were relying on older techniques. We've gotten a lot better at dating things, but the precision and the accuracy of the dating of marine terraces is pretty sound. That's something that's in no way controversial.
Thank you. The person who asked the question said that was a very fascinating answer. Did Morro Rock affect the sand spit?
I would think so. I know that every year, let's go to that. I don't know if we I mean, it's this big obstacle. What's more, I'm gonna capture the screen again. Right, so Morro Bay, or the rock, I guess, Morro Rock is really, it's what's called a tombolo, which is one of my favorite names in geology. I always thought that would be a good name for a cat. Tombolo. Probably not a good name for a dog. But anyway, there it is right there. I can't do better. I don't know why I'm not. This thing is, there we go. Okay. Yeah, so there it is, Morro Rock. So this is called a tombolo. The little body of sand that connects the rock with the coastline is called a tombolo. And under natural, they've fortified it with a road, and I'm sure you've all been out there in the parking lot, but under natural conditions, this would come and go seasonally or annually, depending on how strong the waves were. But yeah, it must have played some kind of role in disrupting the littoral cell. But clearly there's enough sand getting around it to feed it, because there it is. So I'm sure it influences it one way or another, but apparently it doesn't inhibit it much, because that's, again, it's, as my friend Martin he's hard to impress, and he's like, that's an impressive sense, but okay. Okay.
Thank you. At lower stand of the sea 18,000 years ago, can you discuss the idea of an embayment, delta, and sandspit that would have formed far offshore and its migration to the present Morro Bay location over thousands of years with sea level rise?
Wow. That is a beefy question. Well, okay, where to begin? So yeah, the 18,000 years ago, this would have been completely different. There would not have been, there would not have been a sandspit, obviously. So everything you see here, this whole configuration is probably less than 10,000 years, because the maximum advance of glaciers was 18,000 years ago, but really sea level didn't rise to its current level until about 10,000 years ago. So during that time, there must have been, the river system must have extended along the shelf and perhaps fed a delta that would have been offshore, as was asked in the question. As far as whether or not so for example, if you're familiar with Hazard Canyon and Hazard Creek, which is in Montaña de Oro, surfers love that place because there's a huge canyon offshore, just like the Monterey Canyon. So in that instance, what happened definitely was sea level dropped, and it caused Hazard Creek to cut a deep canyon in the continental shelf. And then when sea level rose, it just became this great surf spot. Here, it's not really clear. I don't think there's a big canyon offshore. That doesn't always happen. When sea level drops, whether or not a stream is able to incise across the continental shelf, as it's called, depends on mainly on the steepness of the shelf, but it could also depend a lot on the size of the rivers that are feeding that particular point. As far as I know, there's no big canyon offshore of the Morro Bay estuary. So it may have just been, a river extended across the shelf, and it didn't necessarily carve a canyon, but it obviously drained into the ocean. So I haven't seen evidence. I just collaborated, I was a co-author on a paper, and we had to assess whether or not the Santinez River incised across the shelf. So reviewers were being very difficult, and I got a bathymetric map, and it shows there's all along this area, canyons are rare on the shelf. So so something like Monterey Canyon or Hazard Canyon did carve, incise across the shelf, but Los Osos Creek may not have been able to do that, as far as I know.
Thank you for answering that one. And then this one is looking for clarification on that last photo of the marine terraces at Montaña de Oro. It says, in the photo of the Montaña de Oro marine terraces with their ages, what is the first number on the left of the slash with the age to the right?
Great. Sorry about that. Geologists, we have defined what are called, so the way that they figure the best chronology, or the most extensive chronology for glacial periods and interglacial periods, comes from sediment cores. They take these sediment cores, they look at the oxygen isotopes in the little beasties that they get in the kettle. By beasties, I mean one-celled animals. So pretty much all the glacial, interglacial periods are defined by the oxygen isotope geochemistry of these tiny little organisms. And when they started collecting these sediment cores, they just said, okay, this is the one at the top, we'll call this 1. So right now we're in oxygen isotope stage 1, and then oxygen isotope stage 2 would be the glacial period that preceded the current interglacial period, and then oxygen isotope stage 3 would be the next glacial period, and so on. So these are referred to oxygen isotope stages. So 13 is oxygen isotope stage 13, which was an interglacial that happened 480,000 years ago. The reason these are 5A and 5E is because oxygen isotope stage 5 was a very prolonged high stand, so they subdivided it into A, B, C, D, and E. So that's what those numbers mean. Good question. Sorry, I didn't explain that.
Thank you for clarifying that. And it looks like we just have one more question left. Why don't the creek sediments coming into Morro Bay get trapped by the sand spit and silt up the bay?
They do. I mean, every year, I have pictures, but it would take way too long to find them. Every year there's a dredge out there. if you live in Morro Bay in the summer, every year there's a dredge taking all the silt out of that bay to keep the harbor functioning. If not, you wouldn't be able to park the ships in there. But they're usually out there like July and August, as far as I know. I've been here 20 years, and they're always there in that time of year. So yeah, it is silting up, but it would probably fill up under natural conditions, but we need a harbor. There's no other good harbor between like from here to, I don't even know where, way down south. I guess the San Luis Obispo and all that's not regarded as being a good harbor. But, anyway.
Awesome. Thank you. It looks like we're at the end of our questions. So I just want to say a huge thank you for joining us. That was such an awesome presentation. I know we've been wanting, a lot of people have requesting something like this for a while. So thank you so much, Tony, for joining
You're welcome.
us.
Thank you guys for being here, and have fun. Enjoy the
Thank
park.
you.